Welcome to Late Night History. Tonight, you don't have to go anywhere. You don't have to do anything. You can let your shoulders drop, let your jaw soften, let the weight of the day settle out of your hands. We're going underground tonight, slowly, the way you'd walk down into a cellar by candlelight, one step at a time, letting your eyes adjust before you take the next. There's no hurry here. There's nowhere we need to be by any particular moment. The caves we're going to wander into have been waiting for millions of years, and they will keep waiting, patient as stone, long after you've drifted off. So let yourself sink. Let the room around you grow quiet. And come with me down into the dark, where the earth keeps its oldest, strangest secrets. We begin not with the biggest cave, or the deepest, or the most beautiful. We begin with the one that breaks the first rule we ever learned about life itself. The rule is simple, and you've known it since you were small enough to press a seed into a paper cup and set it on a windowsill. Life needs the sun, plants reach for it, animals eat the plants, and the whole green machine of the world runs, in the end, on sunlight. That's the rule. And in a small, sealed pocket of rock beneath the south of Romania, that rule is quietly, completely broken. Picture a flat, unremarkable stretch of land near the town of Mangalia on the Black Sea coast of Constanța County. Nothing about the surface gives it away. There's no yawning mouth in a hillside, no dramatic gorge, nothing a passerby would ever notice. For 5.5 million years, there was nothing to notice because the thing we're looking for was sealed beneath a layer of clay so dense that nothing could pass through it. Not water, not air, not light, not the smallest hint of the world above. And then, in 1986, people came with machines. They were doing the most ordinary kind of work imaginable. They were testing the ground, doing groundwork for a power plant, the sort of survey that happens in thousands of forgettable places every year. They were checking whether the earth here could bear the weight of what they meant to build. And in the course of that testing, almost by accident, they broke through into a void, a space below. A cave nobody had ever entered, nobody had ever named, nobody had ever imagined was down there at all. What they had found, though it would take years to understand it, was a sealed world. We call it Peștera Movile now. Movile Cave. And the scientist, whose name is bound to it more than any other, is a Romanian biospeleologist named Șerban Șarbu, who would spend his life trying to understand what lived in the dark down there and how on earth it had come to be. Now here is the first strange thing, and it's worth sitting with because it's the foundation of everything else. That layer of clay above the cave wasn't just a lid, it was a seal, an almost perfect, almost total seal, and it had been in place for somewhere between 5 and 5.5 million years. To get a sense of that span, you have to let your mind stretch in a way it isn't really built to. 5.5 million years ago, there were no modern humans anywhere on the planet. Our distant ancestors hadn't yet stood upright in the way we'd recognize. Whole species had come and gone, mountains had risen and worn down, the coastline of that very sea had shifted and shifted again. And through all of it, this little pocket of life beneath the clay just kept on, sealed off, breathing its own air, eating its own food, knowing nothing of the sun that ruled everything above it. And that air. Oh, that air would kill you. Imagine taking a breath at the surface right now. The air you're drawing in, the air filling your lungs as you lie there, is about 21% oxygen. That's the number your body is built around, the comfortable margin you never have to think about. Down in Movile, the air holds only about 7 to 10% oxygen, less than half of what you're breathing, the kind of thin, starved air you'd find high on a mountain peak, except this is at the bottom of a cave. And mixed into it is carbon dioxide, far more than the surface holds, 2 or 3%, sometimes more. And then there's the part that makes it not just thin, but poisonous. Hydrogen sulfide, methane. Hydrogen sulfide is the smell of rotten eggs, that sulfurous reek that makes your nose wrinkle and your stomach turn. In small amounts, it's just an unpleasant smell. In the amounts that hang in the air of Movile Cave, it's a poison. To you, to me, to almost every animal that walks the surface, that air is simply death. A few breaths and you'd feel it. More than a few, and you wouldn't be feeling anything at all. And yet the cave is alive, crowded with life by its own strange measure. Which brings us to the rule it breaks, and to the question of how anything can live somewhere the sun has never touched, and the air itself would kill you. The answer is a word you may not have heard before, so let's take it slowly, and let me hand it to you with something every day to hold on to. The word is chemosynthesis. Break it into its pieces. Chemo for chemistry, for chemicals, synthesis for making, for building. Chemical building. Up on the surface, almost everything runs on photosynthesis. Photo for light. Plants take sunlight and water and air and build sugar, food, the bottom rung of the whole ladder of life. Take away the sun and, by every rule we learned, the ladder should collapse. Nothing to build the first rung, nothing for anything else to climb. But in Movile there is no sun to build that first rung, so something else does it. Down in the warm, sulfurous water of the cave, there are bacteria. Tiny, invisible, countless. And instead of drinking in sunlight the way a leaf does, these bacteria feed on chemistry. They take the hydrogen sulfide, that poisonous, rotten egg gas, and the methane, and they pull energy out of them directly. They eat the very things that would kill you. The poison in the air is, to them, a feast. They oxidize the sulfur and the methane, and in doing so they build the food, the sugar, the first rung of the ladder, with no sunlight involved at all. Think of it like this. Up here, a green plant is a little solar panel soaking up light and turning it into food. Down there, those bacteria are something stranger. They're more like creatures that have learned to eat smoke to make a meal out of fumes that would choke anything else and to thrive on it. They are the entire foundation of a living world built not on light, but on poison, and you can see them. They don't stay hidden. On the surface of that warm, still, sulfurous water, the bacteria gather into floating mats, pale, drifting films of life. Microbial mats, the scientists call them, though the people who've actually crawled down there have a blunter, truer name for it. They call it the scum. A skin of living bacteria floating on black water in total darkness, and that scum, that quiet pale film, is feeding an entire ecosystem. Because where there's food, there's something to eat it. And this is where Movile stops being just a chemistry experiment and starts being a small, sealed kingdom of creatures. Scientists have identified somewhere around 48 to 57 species living down there. And here's the figure that makes biologists lean in close. Of those, the great majority, commonly said to be around 33 to 37 of them, are endemic. Endemic is a lovely, precise word, and it simply means found nowhere else on Earth. Not nowhere else in Romania, not nowhere else nearby, nowhere else on the whole planet. These are creatures that exist only in this one sealed pocket of poison darkness and have never existed anywhere else, and if the cave were gone tomorrow, they would be gone with it, utterly and forever. And what creatures they are, blind, everyone. Why would you have eyes in a place that has never, not once, in 5.5 million years, held a single ray of light? Eyes are expensive. They cost energy to build and energy to run, and in a world where every scrap of energy is precious, a body that has no use for sight simply stops building them. Generation by generation, in the long, patient dark, the eyes shrank and vanished. And the color went too. Up here, color is everywhere in fur and scale and shell, but pigment, like eyes, costs something to make, and in a place with no light to be seen by and no light to see, color is pointless. So these creatures are pale, ghost pale, pigmentless, the scientists say, which is just a careful way of saying the dark has bleached them. There's a water scorpion down there, blind and pale, leeches that live their whole lives in the sulphurous water, one of them feeding on the worms that live in the cave with it. Spiders, pseudo-scorpions, which are tiny, pincered creatures, like scorpions in miniature but without the stinging tail. Woodlice, centipedes, springtails, those minute jumping creatures of soil and damp, a whole little bestiary of the colorless and the sightless, hunting and being hunted in air that would kill you, in a darkness that has no bottom and no edge, all of it ultimately fed by bacteria eating poison off the surface of black water. And getting to them is its own ordeal. You don't stroll into Movile. Almost no one is ever allowed in at all. Only a handful of scientists in the decades since the cave was found have ever been permitted to descend. And descend is the word. You go down a narrow shaft into the warm dark, and then it gets harder because parts of the cave are flooded. The passages dip below water, and to go on you have to dive, holding your breath in the dark, swimming through submerged tunnels of stone until you come up again into what the explorers call air bells, pockets of air trapped against the rock ceiling. You surface into one of these little chambers, gasping, and the air you've surfaced into is that same thin, poisonous, rotten egg air. You've held your breath to swim to a place where breathing is its own danger. There's something almost unbearable about that image, and something fitting too. The whole cave guards itself. So, here it is. We share this planet with an ecosystem that has never seen the sun, that breathes air that would kill us, that runs on poison instead of light. And we only found it by accident while testing the ground for a power plant. And now we come to the part that scientists still cannot agree on, because Movile is not a closed question. It's an open one, and it has stayed open for decades. The argument is about how these creatures got there and how long ago. One view is the clean and beautiful one. It says the animals were sealed in around 5.5 million years ago, when the clay closed over them, and that they have been evolving in total isolation ever since. Cut off from everything. A perfect, natural experiment in what life does when you lock it in the dark and walk away for 5 million years. By this view, every blind leech and pale springtail is a child of that sealed world, shaped entirely by it. But other researchers push back. Some of these lineages, they argue, may be far older than the seal. Relicts, they call them, survivors from a much older world that found their way down and held on so that the cave isn't a 5 million year experiment, but a refuge for things older still. And others wonder whether the seal was ever quite as perfect as it looks. Maybe a little exchange happened here and there, more recently than we think. Maybe a trickle of something got in or out. And beneath all of that sits the deepest question, the one that goes to the very heart of why Movile matters. Is this ecosystem truly completely independent of the sun? Is it really running on nothing but the chemistry of the rock and the water and the poisoned air, with no help at all from the world above? Or does some trace of surface nutrients still seep down through that clay, some faint inheritance of sunlight smuggled in, propping up a world that only looks self-made? That argument is genuinely unsettled. Scientists who have spent their lives on this cave do not all agree on the answer. And that uncertainty is exactly why people far beyond Romania care about a small flooded cave near Mangalia. Because if life can build itself in total darkness on chemistry alone, with no sun at all, then the places we might find life are not limited to sunlit surfaces. Out past the asteroid belt, there are moons with oceans hidden beneath shells of ice. Europa, circling Jupiter. Enceladus, circling Saturn. Dark oceans, sealed under ice, never touched by sunlight, possibly warmed and stirred by chemistry from below. And Movile is the closest thing we have to a working model of what life might do in a place like that. An Earth analogue, the scientists call it. A small, poisoned, sunlit rehearsal for the kind of life that could be waiting on another world. We study a flooded cave in Romania to learn how to look for life on the moons of distant planets. There's a kind of wonder in that I hope you can feel, even as you're drifting. Before we go deeper, let me ask you something, gently, the way you'd ask in the dark. Wherever you are tonight, whatever country, whatever city, whatever quiet room, I'd like to know. Tell me where in the world you're listening from. It's a small thing, but it makes this dark feel a little less lonely, knowing you're out there. And if you're new here, if you've only just found your way to late night history, you might want to subscribe, so the next slow journey finds you when you need it. There's no rush. The comment will keep. You can leave it in the morning if your eyes are already heavy. Because that's the promise tonight. We're going to walk slowly through 7 of the strangest caves on this whole planet. Not the biggest for the sake of bigness, not a list of records to memorize. 7 places where the Earth does something so strange that the scientists who study them, the people who've devoted their careers and risked their lives to crawl inside, still argue about what they're seeing. 7 rules of the world, quietly broken in the dark. And you don't have to stay awake for all of them. You can drift off anywhere along the way. The caves will keep. I'll keep walking slowly, and the dark will stay comfortable around you. So let's leave Movile now. Let's let that sealed, sunless world close behind us with its blind leeches and its poisoned air and its argument that may never quite be settled. And let's cross half the world, from a small, flooded cave in Romania to a chamber buried deep beneath the desert of northern Mexico, because the next rule we break is a different one entirely, not about life, about stone, about how big a single crystal can possibly grow. Picture the desert state of Chihuahua in the north of Mexico, hot, dry, hard country, and beneath it, a mine. The Naica mine, where for many years men went down into the earth to pull out lead and silver and zinc. Mining is wet, deep work. The lower you go, the more groundwater you meet, hot water seeping in from the rock around you. And to keep the tunnels open, you have to pump that water out, constantly holding back the flood so the work can go on. In the year 2000, 2 miners, the Delgado brothers, were doing exactly that. Draining water from a chamber some 300 meters down, around 1,000 feet beneath the surface, in the warm dark of the mine. Pumping out the groundwater so they could get at the rock. And as the water level dropped, as the flooded chamber slowly emptied, something began to emerge from beneath the surface of that retreating water. Something that, by the time the chamber stood drained and open before them, must have stopped them where they stood. Crystals. But not the kind you keep on a shelf. Not the kind you hold in your palm. Beams of crystal, vast, translucent shafts of stone crossing the chamber like fallen pillars, like the rafters of some giant's house, the largest of them 11-12 meters long. Picture that, a crystal as long as a city bus. A single crystal you could not put your arms around, that you could walk the length of and grow tired before you reached the end. Some of them weighing as much as 55 tons, a single crystal heavier than a loaded truck, and clear and pale and shining in the lamplight that had never touched them before. They are selenite. Selenite is a form of gypsum, which is a soft, common mineral, the same stuff that, ground up, makes the plaster in your walls and the chalk teachers once wrote with. ordinary gypsum, nothing rare about the ingredient at all. And that's part of what makes the chamber so astonishing. The miracle here isn't a rare material, it's the size. Gypsum is everywhere, but gypsum almost never grows like this. Somehow, in this one buried room beneath the Chihuahuan desert, the most ordinary of minerals built the largest natural crystals ever found. We call the place Cueva de los Cristales, the cave of crystals, and it nearly cooks you alive. Because here is the next thing, the thing that makes studying this room one of the most punishing tasks in all of science. That chamber, when it was found, sat at about 58 degrees Celsius, 136 degrees Fahrenheit, hotter than the hottest summer day you've ever endured, hotter than a sauna, a steady, relentless baking heat that doesn't let up because you're 300 meters underground and there's nowhere for it to go. And the air is nearly saturated with water. 90 to 99% humidity, so thick and wet you could almost drink it. That combination, that much heat and that much moisture, is lethal to an unprotected human in a matter of minutes. It isn't just uncomfortable, it will kill you. The heat and the humidity together stop your body from cooling itself. Your sweat can't evaporate in air that's already nearly full of water, so your body's one trick for shedding heat simply fails, and your core temperature climbs and you fade fast. A few minutes in that room without protection and a person would collapse. So the scientists who wanted to study the crystals had to become something close to deep sea divers, except the thing they were diving into was heat. They built suits packed with ice, suits with their own cooling systems, suits to keep a sliver of survivable cold around the body. They wore respirators to breathe air that wasn't full of scalding moisture. And even so, even armored against the room, they could only last 15 or 20 minutes at a time before they had to retreat to the surface, to cool, to recover before going down again. Imagine that. The most beautiful room ever found inside the earth, a cathedral of giant shining crystals, and you can only stand in it for the length of a coffee break before it begins to kill you. And here we arrive at the first great argument of this place. How long did these crystals take to grow? Because they didn't appear overnight. Crystals grow slowly, atom by atom, as minerals come out of water and lock themselves into a pattern. And the bigger the crystal, the longer the patience required. For crystals this size, the estimates are staggering, hundreds of thousands of years. Commonly you'll hear figures of 500,000 years or more. 500,000 years of slow, silent growth in the warm dark, while the world above ran through ice ages and warm ages, while whole species rose and fell, while everything we'd call history happened and ended, the crystals just kept growing, atom by patient atom, in their flooded, scalding room. And the secret of their size isn't speed, it's stillness, it's stability. Here's the heart of it, and let me hand you the chemistry the same gentle way. The chamber was filled with water, hot water, saturated with minerals, and held, crucially, at a temperature that barely moved. Right around 58 degrees Celsius, and holding there year after year, century after century, for ages on end. And 58 degrees turns out to be a magic number for gypsum. There's a related mineral called anhydrite. Anhydrite and gypsum are close cousins, the same basic stuff in slightly different forms, and there's a temperature where one turns into the other, a kind of dividing line. Above that line, anhydrite is stable. Below it, gypsum is, and the water in this chamber sat right at the edge of that line, just below the point where anhydrite converts to gypsum in a slow, gentle, endless trickle. Not a flood of minerals crashing out all at once, which would have made many small crystals racing each other for the material, but a slow, patient seeping, atom by atom, onto a few growing crystals over and over for 500,000 years. That's the lesson the chamber teaches, and it's a soothing one to fall asleep on. The giants weren't made by force or by speed. They were made by patience, by a temperature that refused to change, by stillness held so long it built shafts of crystal as long as buses. Slow and steady in the warm dark, while everything above changed and changed and changed. Stability, not speed, made the giants. When the mine finally fell quiet, when the pumps that had drained the chamber were eventually switched off, the groundwater came creeping back. It rose through the tunnels, filled the chamber again, closed over the crystals, and returned them to the warm mineral bath they'd grown in, sealed away once more. And there's an argument even in that, a quiet, almost tender one. Was it right to let them flood? Some felt that re-flooding them was a kind of preservation, returning the crystals to the conditions that made them, keeping them safe in their groundwater bath, perhaps even letting them go on growing. Others mourned the loss of the chance to study them, the door closing on one of the strangest rooms ever found. To preserve them, you had to bury them again. To keep them, you had to give them back to the dark. But the strangest argument of all, the one that's still genuinely unsettled, isn't about the crystals themselves. It's about whether something might have been alive inside them. Because crystals, as they grow, don't always grow perfectly. Sometimes, as the mineral locks itself into place, it traps a tiny bubble of the water it grew in, a flaw, a pocket, a droplet of ancient liquid sealed inside the solid crystal. The scientists call these fluid inclusions, little prisons of water locked in stone, untouched, since the moment the crystal closed around them, which might be tens of thousands of years ago. And in 2017, a researcher named Penelope Boston, associated with NASA, reported something that stopped people in their tracks. She said that inside those fluid inclusions, inside those tiny, sealed droplets within the giant crystals, there were microbes. And not just the remains of microbes, living ones. Microbes that had apparently been trapped, dormant, sleeping inside the crystal for an immense span of time, perhaps 10,000, perhaps 50,000 years, and that could, she reported, be revived, woken, coaxed back to life after their long sleep in the stone. Sit with that for a moment in the warm dark behind your eyes. Something alive, sealed inside a crystal, sleeping through the rise and fall of 50,000 years. Waiting, in a way, the way the cave itself waits. But you must understand, this is a claim and it is contested. It is exactly the kind of result that science treats with great care because the implications are so large and the chance of error is real. Critics raised the obvious worry: contamination. When you go into a chamber, even in your eye suit and your respirator, you carry life with you. On your skin, on your gear, in the air you bring. And modern microbes are everywhere, tough and patient and quick to creep into any sample. So the question became and remains, are these genuinely ancient survivors, sleepers woken from 50,000 years in the stone? Or are they modern microbes, ordinary contaminants, that slipped into the sample somewhere along the way, and only seem ancient? The result was reported, but at the time it was not fully published, not fully confirmed by the careful, slow checking that science demands. It hung, and in some sense still hangs, in that honest space between wonder and doubt. And that is where we'll leave the crystals for now, in their flooded chamber 300 meters beneath the Chihuahuan desert, sealed in their warm bath, with their sleeping maybe microbes locked in droplets of 50,000-year-old water, and the scientists who found them still unable to agree on whether anything in there is truly alive, or truly ancient, or both, or neither. 2 caves now behind us in the dark. A sealed Romanian world that breathes poison and runs on chemistry instead of sun. a scalding Mexican chamber where the most ordinary mineral grew into the largest crystals ever found, slowly, patiently, over 500,000 years of stillness. 2 rules broken, 2 arguments that refuse to settle. And we've barely begun to go down. The pumps. That is where the Naica story bends. The crystals grew because the chamber flooded and stayed flooded, because the water held at exactly the right temperature for exactly the right span of time, because stillness and saturation and a kind of geological patience we have no cultural equivalent for built something that simply should not exist at the scale it does. But the mine needed to operate, and operating meant pumping the groundwater out. And so the chamber was accessible briefly, historically briefly. For the few years the pumps ran and the water stayed low enough that a suited, ice-cooled researcher could squeeze inside and endure the heat for 15 minutes at a stretch, 15 minutes, to study a space that took 500,000 years to make. And then the mine company made a decision, or had a decision made for them, and the pumps slowed, and the water began to return. There are people who argue the reflooding was a good thing. The crystals had been exposed. Tourists, however few and controlled, had breathed on them. Researchers had touched and sampled them. The original conditions that made the giants possible were the sealed, flooded, stable conditions, and what was found in those conditions, that still contested hint of dormant life in the fluid inclusions, could only survive if those conditions were restored. Reflooding the cave is, in this view, the right act of conservation. You found it, you documented it, you sealed it back in. Let the next 50,000 years do whatever they will with it. Others are less settled about this. Once the chamber is reflooded, access is effectively over. The unanswered questions about Penelope Boston's reported microbes, the contamination dispute, the peer review that was never quite completed, the replication that never came, all of that becomes permanently harder to revisit. Not impossible, perhaps. Divers can reach flooded places. But the conditions that allow careful biological sampling in a 48 degrees Celsius chamber, wearing an ice suit and breathing through a respirator, with less than 20 minutes before your body begins to fail, those conditions are already at the edge of what humans can physically do. Add water, and the problem compounds itself into something very close to unanswerable. And so the argument shifted from whether the microbes were real to whether we locked the door before we finished asking the question. The Naica crystals sit now in their warm bath. The water has returned. The chamber is sealed. And the thing Penelope Boston spent years of her career trying to establish, that something genuinely ancient can survive inside a crystal, that the geological record keeps biological passengers the way amber keeps insects, that frozen fluid inclusions are not dead space but sleeping archives, that thing is still not resolved, still not confirmed, still not refuted. 300 meters below the Chihuahuan desert, the largest natural crystals ever found rest in their flooded dark, and in some of them, or possibly none of them, or possibly only in the samples already collected and sitting in a laboratory somewhere, something may or may not be waiting. We leave them there, and we travel east, southeast, across the Pacific, and down into a country shaped by limestone, by deep jungle, by rivers that disappear underground for kilometers and reappear somewhere unexpected, and by a geology so wet and so old that the rock has been dissolving steadily for tens of millions of years, wearing away from within, carving spaces that accumulate into chambers and passages on a scale that strains the imagination of anyone who has only ever lived above ground. Vietnam. The province of Quang Binh. And inside Phong Nha-Kẻ Bàng National Park, a mountain so riddled with passages that a man who lived near it for years had heard the river going into it, but had never told anyone who might want to go after it. His name was Ho Khan. He was a local man, a hunter, and in 1991 he found the entrance to Hang Son Doong. He found it the way most caves get found by ordinary people rather than geologists or cavers. He was walking in the jungle and he heard something. Wind, strong enough to move him, coming out of the earth. He looked, and there was a gap in the rock, and from it came a wind and a roar, because below the gap, far below it, was a river, the Rao Thuong, the one that had been carving the mountain from the inside for millions of years, still moving, still cutting. He looked down into the dark and the noise and the wind, and he retreated. You would retreat too. And then, because the jungle in that region is dense and difficult and the years were not easy, and because this was 1991 in a remote province with no obvious infrastructure for international cave exploration, he more or less kept it to himself, or he lost the location, which accounts vary on. 17 years passed. In 2009, a British caving team, Howard and Deb Limbert, working with the British Cave Research Association, had been exploring the cave systems of Phong Nha-Kẻ Bàng for years. They were shown the entrance, or they found it again, with Ho Khan's help. Either way, they went in. And what they found inside in those weeks of surveying in 2009 was something that exceeded any expectation formed by any previously mapped cave system on Earth. The main passage of Son Doong is 200 meters high. Let that number sit for a moment. 200 meters. A 40-story building fits inside with room above it. The width reaches 150 meters, and it runs for kilometers like this, not narrowing significantly, not dropping to a crawl you have to belly through, but staying vast, staying cathedral-scaled for distance after distance after distance. The Limberts and their team measured and mapped and came back with numbers that were, when published, immediately disputed in the way that genuinely large discoveries get disputed, not out of bad faith, but because the numbers are hard to trust when they are that far outside the range of previous experience. But the numbers have been confirmed. Son Doong is the largest known cave passage by volume on Earth, and it is not close. The Rao Thuong River, which carved it, still runs through part of it underground, continuing the work it started millions of years ago, the slow, patient dissolution of limestone by slightly acidic water, the same chemistry that makes stalactites and stalagmites and all the other formations of any ordinary cave, but here applied at a scale and over a duration that produce something that has to be experienced in person to be fully credited by the senses. But the river and the scale are not the strangest things about Son Doong. The strangest things are the holes in the ceiling, dolins. The word comes from the Slovenian, and it describes a sinkhole, a place where the roof of a cave collapses inward. In an ordinary cave system, this produces a pit, a rubble pile, a place where the surface meets the underground in a rough, messy way. But Son Doong is not an ordinary cave system, and its two dolines are not ordinary sinkholes. They are enormous skylights, openings in the mountain's limestone ceiling 100 meters above the cave floor, through which sunlight falls in great shafts, and through which rain falls, and through which over thousands of years seeds have fallen, and the seeds have germinated, and the plants that grew from them were not small, they were not modest. The dolines of Son Doong have jungles inside them, full rainforest, trees that reach 30-40 meters toward the light coming through the holes in the mountain, figs, palms, climbing plants, ecosystems that from the cave floor look like something pulled from the imagination of a person trying to describe a lost world and failing because the real thing exceeds the description. The plants do not simply grow vertically. Limestone, when it weeps, when groundwater seeps through it and carries minerals to surfaces that are regularly lit, grows a biological skin, algae, moss, and then the higher plants that root in them, all of it angling, reaching, stretching toward whatever light the doline lets in. This growth, plant life shaped by and attached to cave rock, has a name: phytokarst. The rock becomes a garden. The garden is improbable, and at the edge of the doline's light, where the jungle gives way to the deeper dark of the passage, creatures move between the two worlds, or do not move, having committed to the dark completely, having given up the eyes and pigment that light rewards, and become whatever the long dark makes of a living thing when there is nothing to see. Researchers studying Son Doong are still working out which creatures bridge the two worlds, and which have fully committed to the dark passages beyond the dolines. The dividing line between the sun-fed ecosystem and the cave-adapted one is not a wall. It is a gradient, a slow fading of light, and somewhere along that gradient, in the dimming, a creature is either the last thing that can still use the sun or the first thing that has let it go. And then there are the clouds. This is the part of Son Doong that people struggle most to convey in photographs or in descriptions or in anything other than the direct experience of standing inside the cave and looking up and seeing weather. Because Son Doong is large enough and the temperature and humidity difference between its interior air and the cooler outside air coming through the dolines is large enough that clouds form inside the cave. Not mist, not haze, clouds, visible, defined, moving slowly in the airflow that threads through the passage. You are underground inside a mountain, and above you, between you and the ceiling, there is a cloud. Small perhaps by the standards of open sky, but a cloud behaving the way clouds behave, forming and drifting and occasionally releasing what it carries. This is not a metaphor. This is meteorology operating underground. The cave is large enough to have its own microclimate. The conditions inside it generate precipitation. Son Doong has weather. And near one of the dolines there is a wall. Not a wall built by anything with hands. A calcite wall, grown slowly by the same mineral processes that make all cave formations, but grown here to a height of 90 meters. The cavers who documented it, wanting to name what they found, called it the Great Wall of Vietnam. It is the largest known speleothem of its kind, a single, continuous calcite barrier across the passage. Getting past it requires climbing it, which is its own kind of vertical journey, inside a cave that is already its own kind of impossible. Below the Great Wall, in dry pools along the passage floor, are cave pearls, small rounded formations, white or cream-colored, formed when mineral-rich water drips into a shallow basin, and the agitation of the drip coats a small nucleus with layer after layer of calcite, perfectly, spherically, the way a real pearl forms in a real oyster, which is the same process in inverse, life coating irritation into beauty, geology coating motion into stillness. The cave pearls of Son Doong are not unique to this cave. Many caves have them, but Son Doong's are large, and they sit in basins inside the largest known cave passage on Earth, which gives them a context that makes them feel less like a geological footnote and more like an offering. Now, the open question. In 2019, divers entered the flooded passages of Son Doong and found a connection. Underwater, below the walking and climbing sections of the cave, below the dolines and the jungle, and the clouds and the Great Wall, Son Doong connects to another cave, Hang Thung. The two systems are linked by a submerged passage, and the implication of that link is significant. If the two cave systems are connected underwater, then what is measured as Son Doong on one side and Hang Thung on the other may in fact be parts of a single, larger system, one that, when fully accounted for, would substantially exceed even Son Doong's current dimensions. The combined volume, if the surveys are eventually completed and the underwater connections fully mapped, would produce a number that makes Son Doong alone look like an understatement. But the surveys are not complete. The underwater passage is difficult to map safely. The question of how large the system truly is remains open, genuinely open, in the way that scientific open questions are different from rhetorical ones. It is not open because no one has bothered to close it. It is open because closing it requires time and resources and the willingness to put divers into flooded passages inside a mountain in a remote national park in central Vietnam, and those conditions are not easily met. So the measurements stand where they stand. The largest known cave passage, the largest known single cave volume, and possibly, almost certainly, connected to something larger beneath. Håkan heard the wind coming out of the earth in 1991 and looked down into the roaring dark and walked away. He knew something was there. He did not know what. Neither, entirely, do we. And we keep moving. West again, and north, crossing the Pacific back and arriving at a desert landscape that does not look, from any surface perspective, like a place concealing something remarkable. The surface of the Guadalupe Mountains in southeastern New Mexico is scrub and limestone, and a dry, hard beauty, the kind of landscape that asks something of you before it offers anything. But below this landscape, accessed until the late 1980s only through a small, windy hole in the rock that local cavers knew as a blowhole because of the distinctive breath it exhaled, is one of the strangest sealed environments in the United States, Lechuguilla Cave. For decades, the blowhole at the surface was a minor curiosity. A small opening, a draft, the suggestion of something below. Cavers knew it. They had mapped a modest system. But the major passages, the ones that would eventually make Lechuguilla one of the most scientifically significant caves on Earth, were blocked, filled with rubble. A pile of breakdown and debris that seemed to say, "This is as far as you go." And for a long time, that was true. In 1986, the same year, Serban Sarbu was being lowered toward Peștera Movile through a concrete shaft in a Romanian field. A group of cavers in New Mexico were digging. Not excavating with any institutional backing, not with a research mandate, just digging because cavers dig at rubble piles when the draft from behind the rubble tells them there is more. The draft at Lechuguilla's blowhole had always been strong. Something behind the rubble was breathing. So they dug, and after weeks of work, hauling rock out by hand and bucket, they broke through into a descending passage that kept going down, 489 meters down eventually. 240 kilometers of mapped passage, eventually, which makes it one of the deepest and longest caves in the United States, though the mapping has never been declared finished, and the surveyors who work it keep finding more. The thing about Lechuguilla is that it keeps opening. You map a passage, and the passage leads to a room, and the room has a crack in the floor, and the crack leads to another passage, and on it goes, thousands of meters below the Guadalupe surface, in a cave that is by every practical measure still being discovered decades after the rubble was cleared. But the depth and the length are not why Lechuguilla rewrote the textbook. The reason Lechuguilla changed how geologists think about caves is what made it, the mechanism, the process by which all those meters and all those kilometers of passage came to exist. Because when you look at an ordinary cave, one you might visit on a family holiday, with stalactites and stalagmites and the slow drip of water, you are looking at the product of carbonic acid. Rainwater absorbs carbon dioxide from the atmosphere, becomes weakly acidic, and as it seeps through the limestone from above, from the surface downward, it dissolves the rock it moves through. Over enough time, it eats passages and rooms and eventually produces what we call a cave. This is speleogenesis, cave making, and the textbook version of it is top-down. Rain falls, acid drips, rock dissolves, caves form. Lechuguilla is not top-down. The acid that made Lechuguilla came from below. Beneath the Guadalupe Mountains, deep in the earth, are ancient oil and gas deposits, the remnants of organic material that accumulated in a long-vanished sea. And from those deposits, rising slowly through cracks in the rock, comes hydrogen sulfide, the same gas that made Mobile's air toxic, the same gas that the bacteria in Movile's microbial mats eat for energy. Here, in the Guadalupe, it rose through the rock and met oxygen, and the combination of hydrogen sulfide and oxygen produces sulfuric acid, not carbonic acid, sulfuric, one of the most aggressive acids known, and the sulfuric acid rising from below ate the limestone from the inside out, from the bottom up, chewing passages and rooms, not downward from the surface, but upward, or laterally, or in any direction the acid happened to reach. The cave was made from the inside out. The water carved nothing here. The rain played no role. Lechuguilla is the product of underground chemistry, rising fumes, geological belching from depth, and the result is a cave system so geometrically strange, so different in shape and structure from the top-down model, that when geologists first worked it out, it changed the definition of what a cave could be. This is what scientists call hypergenic speleogenesis, cave formation from below. The discovery that Lechuguilla was a hypergenic cave was not simply an interesting geological footnote, it was a paradigm shift. If Lechuguilla formed from below, then other caves might have too, caves that hadn't been examined with that possibility in mind. The model of rain and runoff dissolution was not wrong exactly. It describes many caves accurately, but it is not the only way. The Earth, it turned out, had been making caves in at least two fundamentally different ways, and we had only been looking carefully at one of them. And the formations inside Lechuguilla are, in part, the product of that different chemistry. Gypsum, which is what selenite is, which is what the giants of Naica are made of, appears here too, but in wildly different shapes. There are gypsum chandeliers, curling formations that hang from the ceiling in mineral arcs and loops, looking less like anything geology produces than like something a sculptor made with reference to marine biology. There are soda straws, hollow calcite tubes, so thin and fragile they break at a touch, growing from the ceiling like the world's most improbable and delicate stalactites, each one a tube through which mineral-saturated water once moved slowly enough to deposit its load at the very tip, millimeter by millimeter, over time scales that make a human life feel like a rounding error. And then there are the snotites. The name is not elegant, but it is accurate. Snotites are biofilms, colonies of microorganisms that drip from the cave walls and ceiling in pendulous, glistening strings that look exactly as the name suggests. They are alive. They are actively producing acid, sulfuric acid, the same acid that made the cave, because the microbes in the snotites are chemolithotrophs, organisms that eat minerals, that extract energy from the chemical difference between sulfur compounds and oxygen. And the waste product of that eating is acid. The snotites are continuing the cave's formation. They are the cave eating itself, slowly from within. If you put a drop of snotite on your skin, it would burn. The pH of a snotite is close to 0. Battery acid, dripping gently from the walls of a quiet underground room in New Mexico, entirely indifferent to your presence. The microbes of Lechuguilla are not just the snotites. They are everywhere in the cave, in the walls, in the water, in the sediment, in every surface that has not been touched by human hands. And Lechuguilla has been very carefully protected from human hands, more carefully than almost any other cave on Earth, because the people who mapped and studied it recognized early that they were inside something sealed, something that had been cut off from the surface and from surface contamination for millions of years, and that what they were walking through was a biological archive, a collection of living things and chemical environments that reflected the world as it was before humans changed the chemistry of everything they touched. Access to Lechuguilla is locked. You cannot visit it on a tour. You cannot visit it without institutional affiliation and a specific research or survey purpose that has been approved by the National Park Service. Each expedition is small and strictly controlled. The footprints already inside the cave are considered an environmental impact, something to be minimized and tracked. The cave is pristine in a way that almost no environment on Earth can still claim to be, and that pristinity is the point, the scientific point, because what lives in an environment untouched by modern humans tells you something about the world before modern humans. It is a baseline, a reference point, a before, and the before is strange. Hazel Barton is a microbiologist who has worked in Lechuguilla. She and her colleagues collected samples from the cave's walls and sediments and brought them back to the laboratory, and in those samples they found bacteria, many species of bacteria living in the dark, eating minerals, doing what chemolithotrophs do. None of this was surprising. Movile had already shown that sealed dark environments can support thriving microbial communities. Lechuguilla was sealed and dark and rich in the chemical energy gradients that bacteria like this prefer. Of course there were bacteria, but then they tested the bacteria for antibiotic resistance. The bacteria in Lechuguilla are resistant to antibiotics, not to one antibiotic, to many. One strain in particular, Penibacillus, a genus of bacteria, showed resistance to a range of modern antibiotics. Resistance mechanisms that human medicine has spent the better part of a century worrying about, fighting, trying to stay ahead of, building new drugs to overcome. Resistance to drugs that were invented in laboratories in the 20th century developed in response to the bacteria of the surface world, tested on bacteria that humans interact with. The bacteria in Lechuguilla have never met humans. They have been sealed, isolated, cut off from the surface for millions of years. They have had no contact with modern medicine, no exposure to pharmaceutical penicillin or its descendants, no reason, by the logic of how we usually think about antibiotic resistance, to have developed the mechanisms to defeat them, and yet they have those mechanisms. What this implies is the argument that Lechuguilla forced into the open and that has not been closed since. The standard story of antibiotic resistance, the one that explains the crisis in modern medicine, is that resistance evolves in response to antibiotics. We deploy a drug. The bacteria that happen to have resistance survive. Their offspring inherit the resistance. We use the drug more, and the resistant bacteria spread. Human medicine created human medicine-resistant bacteria. That is the story. It is well documented. It is happening now faster than medicine can keep up with. But if bacteria isolated for millions of years, bacteria that have never seen an antibiotic in any clinical sense, already carry resistance to those antibiotics, then the story has a different beginning. Resistance is not a response to modern medicine. It is ancient. It was already in the bacteria, in the wild, in the rock, in the sediment of sealed caves, millions of years before any human synthesized the first antibiotic. The drugs we invented to fight bacteria are mimics, or echoes, or parallels of chemical weapons that bacteria have been fighting each other with in the rock for eons, and the resistance to those weapons is similarly ancient, similarly present in the bacterial world, regardless of what medicine does. We didn't create the arms race. We joined one that was already millions of years old. The implications of this for how we respond to the resistance crisis are significant and contested. If resistance is ancient and ubiquitous, already present in environmental bacteria everywhere, not just in Lechuguilla, then the notion of outrunning it, of developing new drugs faster than resistance can evolve, is perhaps less realistic than we hoped. The resistance is already there, in the soil, in the rock, in the sediment of every sealed cave, waiting not for our antibiotics, but simply continuing to exist as it has always existed, a deep and evolutionary fact about bacteria as a domain of life. Hazel Barton's work did not end the argument, it started it. The question of what Lechuguilla's resistant bacteria mean for medical strategy, for the development of new drugs, for how we understand the ecology of resistance in the wild, that question is active, being argued, being refined, being studied in caves and laboratories and conferences where microbiologists and physicians who rarely share a vocabulary are trying to understand each other across the gap that their different urgencies have created. And Lechuguilla sits sealed beneath the Guadalupe Mountains, still being mapped, still being sampled in the careful, restricted way that something irreplaceable must be sampled. Its snotites still dripping acid, its gypsum chandeliers still growing at the pace of geological time, its bacteria still carrying their ancient resistance in the dark, entirely indifferent to the argument their existence has started above. 340 meters of limestone above them, the desert is dry and quiet. A hawk might cross the sky above the blowhole. The wind through the rubble pile moves in and out, the cave's breathing as it has always breathed, long before any caver dug through to hear what was on the other side. We have passed now through 3 caves that broke the rule of photosynthesis, that showed life does not need the sun as much as we assumed, Movile on its chemosynthetic bacterial mats, Lechuguilla on its chemolithotrophic mineral eaters, and between them Naica with its crystals and its contested passengers, its sleeping maybe life inside the gypsum. 3 sealed worlds, 3 different chemistries, 3 different arguments. And we are only halfway through. The next one breaks a different rule, not about life, but about depth, about limits, about whether we can trust our own measurements when the thing we are measuring keeps outrunning them. We go east from New Mexico and then north past Georgia, the American state, and into Georgia, the country, on the eastern edge of the Black Sea in a region called Abkhazia, where the Arabika Massif rises from the land in the way that limestone massifs do, in great pale ridges that look from a distance like the bones of something old and enormous pushing through the skin of the landscape. The Arabika Massif is riddled with caves. This particular kind of limestone, this particular kind of tectonic history, where plates collided and the rock was folded and fractured and then slowly dissolved by water moving through the fractures, produces cave systems of exceptional depth. Vertical systems, shafts that drop straight down for hundreds of meters with passages between them that then drop again and again in a staircase going into the earth with no apparent reason to stop. For a long time, the deepest known cave on earth was Peștera Cave, also called Veryovkina Cave, in the same Arabika Massif. Peștera held the record for years, a depth of approximately 2,197 meters, measured by successive expeditions that kept pushing lower, kept finding new shafts, kept determining that what they thought was the bottom was in fact a ledge above another drop, 2 kilometers down. The cavers who reached the deepest points of Peștera spent days underground to get there. Not hours, days. Camping in the cave, hauling ropes and gear through cold passages, in temperatures around 5 degrees Celsius, in absolute dark, through spaces that sometimes narrowed to barely passable slots and sometimes opened into rooms large enough to feel like relief. And then, a little to the south of Peștera, in the same massif, a cave called Veryovkina. The name does not translate elegantly into English. It is a Russian name honoring a caver. And Veryovkina had been known, mapped to a considerable depth, for years before 2018. But in 2018, a Russian expedition pushed further than any before. They rigged ropes down vertical shafts that had previously been thought impassable or not fully explored. They camped underground, as cavers at this depth must, sleeping in nylon hammocks or on foam pads laid on stone, eating food carried down in packs in complete darkness, in cold that does not relent. They pushed a passage that turned into another shaft, and they measured 2,212 meters. Veryovkina Cave, as of that 2018 expedition, is the deepest known cave on Earth. It overtook Peștera by a margin narrow enough to feel like the caves are competing, which in a geological sense they are not, but the proximity of the two records in the same massif suggests something about the Arabika's structure. This is a place where the rock is configured by its history and its geology to produce depth in a way that few other places on Earth manage. The water that moves through the Arabika follows fractures that go very deep. Where the water goes, the cave can follow. And in 2018, the expedition that set the record also documented something that had nothing to do with measuring depth and everything to do with the fact that being at the bottom of the world's deepest cave is a situation with very little margin for error. The cave flooded, not completely, not permanently, but a surge of water fed by rain or snowmelt far above on the Arabika surface moved down through the system, rising through the shafts at a speed that gave the cavers at the bottom very little time to decide what to do. The water came up, by some accounts, more than 100 meters in some sections, flooding passages the team had just come through. The cavers had to move fast, up through a cave they'd spent days descending in the dark, in cold water, hauling themselves up rigged ropes in passages that were flooding around them. They made it out. That sentence is the whole story and barely begins to convey the experience it describes. They made it out of a cave 2 kilometers below the surface during an unplanned flood, in complete darkness, having already spent days underground in cold and exhaustion. And the fact that they made it is partly preparation, partly experience, partly the knowledge that comes from decades of expedition caving in places like the Arabika, and partly the kind of fortune that a reasonable person does not want to depend on at the bottom of the deepest cave on Earth. The dispute about Veryovkina is not primarily about whether the 2018 measurement is accurate. It is about whether it is final, because dye tracing, a technique in which a harmless chemical dye is released into a cave's water system and tracked as it moves through the rock to emerge at springs or other water outlets, suggests that the water moving through the Arabika Massif continues well below what any expedition has reached. The hydrology of the system implies depths of perhaps 2,300 meters or more below the current measured bottom of Veryovkina, below the point where the 2018 expedition turned around and began their survival. If the hydrology is right, there is cave below the cave, unexplored passages below the deepest point any human has reached underground. The record of 2,212 meters is not the bottom. It is the bottom we have found, the bottom of what we can currently access with the equipment and techniques and safety margins that responsible expedition caving allows. The actual bottom, the point where the rock closes in for good and the water has nowhere further to go, may be deeper, possibly significantly deeper, and this is the argument, not about Veryovkina specifically, but about what Veryovkina represents. How deep can a cave go? Is there a limit set by geology, by the pressure of rock, by the point at which passages close to apertures too small for water to follow in any explorable form? Theoretically, yes. In practice, the Arabika keeps implying that the limit is not yet reached. The system drinks surface water and produces it again at coastal springs near the Black Sea at sea level after a journey through the rock that moves through depths no expedition has tracked in full. The path the water takes is the path a cave might follow. And we do not know the whole path. We have mapped the surface of Mars. Radar from orbit has produced elevation models of Martian terrain down to scales of meters. We have photographs of Mars from landers and rovers, detailed images of a world 150 million kilometers away. And we have not mapped the bottom of the Arabika Massif. We have not followed the water all the way from the surface of the limestone to the coastal spring. The floor of Veryovkina Cave is a measurement taken at the end of a multi-day expedition, in conditions that are at the edge of what humans can physically manage, in a system that has already demonstrated its willingness to flood without notice. And below that measurement, the water continues. There is something particular about this that resists easy description. The deep ocean is mapped, at least in its gross features, by sonar. The highest peaks of every continent have been measured. Orbital data covers the planet in fine detail, but the inside of the Earth, the space below the rock, the vertical underworld of the Arabika Massif, is less known to us than the surface of another planet. Not because we haven't tried, but because the trying is limited by what a human body can do in the cold and the dark and the flooding shafts of a cave that is still, in some meaningful sense, deciding whether it is done going down. Cueva and Veryovkina in the same massif, sister caves, rivals in a geological record no one chose to set. The same water feeding both, the same deep fractures that make depth possible, threading through the same pale limestone ridges above the Black Sea. When a new expedition eventually descends past the current record in Veryovkina, or discovers a lower passage in Cueva, the record will shift again. It has shifted before. It will shift. The bottom, as a category, is provisional. It always has been. Hazel Barton is a microbiologist who has spent a significant portion of her career in places most people would not voluntarily enter. Sealed, lightless, chemically hostile caves where the air is poor and every surface is a potential contamination event. Lechuguilla is the cave she keeps returning to, not for the formations, extraordinary as those are, but for the bacteria. And the question those bacteria raised when she and her colleagues began to examine them carefully is one that opened a rather uncomfortable argument about something we thought we understood. The argument concerns antibiotic resistance, and to understand why it unsettled people, it is necessary to understand what antibiotic resistance was supposed to be. The prevailing view for much of the history of modern medicine was that resistance to antibiotics was a consequence of antibiotics. That bacteria developed resistance because antibiotics existed, because the drugs created selective pressure, because any bacterium that happened to carry a gene, allowing it to survive a dose of penicillin or streptomycin, would outlive its neighbors and pass that gene on. This made intuitive sense. It also made resistance a fundamentally modern problem, something that arose in the 20th century when we began manufacturing and distributing these drugs, something that could in principle be managed or contained if we used the drugs more carefully or more sparingly. What Lechuguilla suggested was that this picture was incomplete. The bacteria Barton and her colleagues found in Lechuguilla were genuine cave dwellers. Not surface organisms that had washed in, not contamination from a researcher's glove. Lechuguilla has been sealed from the surface for millions of years. The formations inside it took extraordinary spans of time to grow. The microbial communities living in the rock, living on minerals in the darkness, had been cut off from the surface world and from the surface world's pharmaceutical industry since long before the pharmaceutical industry existed. Long before humans existed, for that matter. And yet, when the researchers tested these bacteria, they found resistance, not to one antibiotic, to many. The species Penobacillus, isolated from Lechuguilla, was found to be resistant to a range of antibiotics, including drugs that were invented in the second half of the 20th century. Think about what that requires you to accept. A bacterium that has been sitting in a sealed cave in the dark, eating minerals, for millions of years, carries the genetic machinery to neutralize drugs that were synthesized in a laboratory in the 1960s. Drugs it has never encountered. Drugs it could not possibly have encountered. There are several ways to think about this. The first, and the one that initially seems most troubling, is that resistance is not a product of modern medicine at all. It is ancient. The genes that confer resistance to antibiotics are not late evolutionary responses to pharmaceutical pressure. They are old genetic architecture present in bacterial populations long before any antibiotic was ever extracted or synthesized, because the chemical compounds we call antibiotics are themselves ancient. Bacteria have been producing antibiotic compounds for hundreds of millions of years as weapons against other bacteria, and bacteria have been evolving resistance to those compounds for just as long. The drugs we invented in the 20th century, it turns out, were not new weapons. They were rediscoveries of weapons that bacteria had already been fighting over for an almost incomprehensible span of time. This reframes the resistance crisis in a way that is both more alarming and, in some sense, more interesting. If resistance is ancient, then it will not disappear when we stop using antibiotics. The genes are already out there, distributed through the microbial world, waiting. The problem is not that we created resistance. The problem is that we created a global environment in which the bacteria carrying those genes are constantly selected for, constantly amplified, constantly spread, from hospital to farm to river to the water, in your pipes, in concentrations and distributions that have no geological precedent. The argument Lechuguilla opened is still running. There are debates about which specific genes were found, how many drugs were implicated, and how precisely to interpret resistance in organisms that live in such radically different chemical conditions from the gut of a human being. There are methodological questions, as there always are when you are trying to study organisms living in a cave that takes days to reach, and that can contaminate itself just from the breath of the person collecting a sample. Lechuguilla is so pristine, so sealed, so carefully protected that even the act of studying it is a controlled event. There are very few research expeditions permitted. Access is tightly restricted. The cave is treated in a meaningful sense as a time capsule, and like any time capsule, its value depends entirely on nothing inside it being disturbed by the people reading it. This is the closed cave conservation ethic in its most serious form. Every footstep in Lechuguilla is documented. Entry requires a permit. The number of people permitted inside at one time is small, and the protocols for preventing contamination are stringent, because researchers understand that what makes Lechuguilla scientifically useful is its isolation, and isolation, once broken, cannot be restored. You cannot untrack a cave. You cannot unbreathe into a chamber that has been sealed for millions of years. The DNA a researcher sheds from their skin, the microbes they carry in from the surface, the oils from their hands on a formation they touch inadvertently, these become part of the record forever, and they corrupt the very silence they came to study. It is a strange constraint. To understand a place, you must enter it, and entering it changes it. Lechuguilla makes this tension unusually stark because the thing you are trying to understand is the microbial community, and the act of entering introduces microbes. The best the researchers can do is be extremely careful, document everything, and work with samples taken under conditions as controlled as conditions in a cave that is 489 meters below the surface of the Earth can be. It is not perfect, but it is the best available approach to reading a document that took 4 million years to write. The gypsum chandeliers still hang in the dark. The snotites still drip their acidic mucus from the walls. The bacteria still move, slowly, through the mineral surface of the limestone, breaking chemical bonds and harvesting the tiny amounts of energy released in a process so slow that their metabolic rate is almost incomprehensible by the standards of any organism accustomed to sunlight and food and warmth. They do not know they are inside an argument. They were here before the argument. They will likely be here long after it resolves. And the cave that formed them, that carved itself from below using sulfuric acid, in a process that reversed the textbook understanding of how caves are made, that preserved in its dark and sterile corridors a biological record of the time before modern medicine. That cave is still there, in the Guadalupe Mountains of New Mexico, sealed and restricted and largely unvisited, keeping its secrets in the way only a place that has been practicing secrecy for millions of years knows how to do. Now, somewhere in the Caucasus region, in the disputed territory of Abkhazia, on the edge of the Black Sea coast, there is a massif of pale limestone called Arabika. It rises to roughly 2,700 meters above sea level. Rain falls on it, and the rain disappears. It falls into the rock following the fractures and dissolution channels that millions of years of chemistry and pressure have opened, and it descends. It descends a very long way. The Arabika Massif contains two caves that between them have traded the title of deepest known cave on Earth back and forth across the last 2 decades. Crubera, also known as Voronya, was for many years the undisputed record holder. Its depth was surveyed at approximately 2,097 meters. To put that in terms that carry the distance, if you drop the Eiffel Tower into Crubera, it would fit, and there would be room below it for another Eiffel Tower, and below that a third, and you would still not have reached the bottom. Crubera held the record, and then Veryovkina was explored to its full depth. In 2018, a Russian expedition descended Veryovkina Cave and reached a point measured at approximately 2,012 meters below the surface. This made Veryovkina the deepest known cave on Earth, surpassing Crubera by roughly 15 meters. The difference is small enough to be almost absurd, a cave that descends for over 2 kilometers, and the margin of victory is 15 meters, about the height of a modest house. But the record is the record, and Veryovkina holds it. What the record does not tell you, and what the number cannot adequately convey, is what it means to actually descend Veryovkina Cave. It is not a journey in the ordinary sense of the word. It is not even a journey in the way that a difficult mountain climb is a journey, where at least the air is breathable and the sky is visible and the direction of danger is clear. Descending Veryovkina takes multiple days. Cavers who make the attempt do not travel to the bottom and return to the surface in a single push. They go down and they camp underground in the cold and the dark, hauling ropes and equipment through vertical shafts and narrow passages, setting up a chain of underground camps at successive depths, resting and eating and sleeping below the rock, while the massif sits above them without sound or light or sympathy. The temperature inside Veryovkina is approximately 5 degrees Celsius throughout most of the system, cold enough to be uncomfortable, cold enough over the course of a multi-day expedition to become a slow drain on the body's reserves, the kind of cold that does not shock you but simply accumulates, a quiet tax paid continuously across every hour underground. The passages are wet in the way that limestone caves in active karst systems are wet. Not just damp, but actively dripping with water moving through the rock above and pooling on ledges and running along the floor, so that the descent requires moving through and past water constantly, and the wetness is added to the cold, and the cold is added to the darkness, and the darkness is added to the effort of descending vertical shafts that have no end you can see from the top. The shafts are perhaps the element that distinguishes Veryovkina most clearly from any ordinary sense of cave exploration. A shaft is a vertical drop, a place where the cave simply goes straight down, and the caver must descend on rope hanging in the dark above a floor that may or may not be visible below them. Some of the shafts in Veryovkina are short enough that they can be managed relatively quickly. Others are long, and the whole point of the cave, the reason it reaches 2,212 meters, while most caves barely scratch a few hundred, is that these shafts are chained together in a vertical architecture of remarkable depth, one pitch leading to another, each one carrying the explorer further from the surface of the Earth and further from any simple possibility of return. In 2018, the same year the expedition reached the current record depth, something happened that illustrated just how easily the cave's terms of engagement could change. A flash flood. Water in a cave does not behave the way water in an open landscape behaves. In an open landscape, you can see a flood coming, you can see the sky change, see the river rising, Hear the sound of water in the distance. Underground, there is no sky. The sound arrives without context. Water that falls as rain on the Arabika Massif, several hundred meters above, can travel through the fractures and channels of the limestone in a matter of hours. And it arrives in the cave not as a trickle, but as a surge, filling shafts and passages with cold water that rises fast and leaves no obvious direction of escape. During the 2018 expedition, water surged through the shafts of Veryovkina and rose approximately 100 meters or more inside the system while cavers were below. This was not a minor inconvenience. This was a situation in which people were in a cave more than 2 kilometers underground, in passages that were filling with water, with the only exit leading upward through the same shafts the water was rising through. The expedition survived. The cavers made it back to the surface. But the flood made visible, with a clarity that no description of depth or temperature or darkness can quite match, the fundamental nature of what Veryovkina is. It is not a place that can be entered casually and exited at will. It is a system with its own hydraulics, its own timetable, its own indifference to the presence of the people inside it. This is the thing about the very deep caves, Veryovkina, Cueva, and the handful of others that have been descended to records within the last few decades, that the numbers do not capture and the superlatives do not convey. They are not just deep. They are deep in a way that makes the depth relevant at every moment, because the only direction that matters for survival is up, and up is very far away, and the route there can be compromised at any time by water or rock, or the simple biological limitations of a human body that has been underground for days. The psychology of it has been described by cavers who have made the descent, and it is not what you might expect. There is the practical absorption of the work itself, the rope management, the anchor placement, the careful movement through passages that require precise technique. This occupies the conscious mind and leaves relatively little space for the more abstract thought that might, in a less demanding context, spiral into claustrophobia or existential unease. But the awareness is there underneath the technique, the awareness of the weight of rock above, of the distance to daylight, of the fact that the cave has already shown once, in 2018, what it does when the water decides to move. The other element of the record that deserves consideration is the element of provisionality. Veryovkina's depth of approximately 2,212 meters is the current measurement. It was reached on a specific expedition by a specific team at a specific moment in the ongoing exploration of the Arabika Massif. But the Arabika Massif is not fully explored. The caves within it have not been mapped to their limits. Dye tracing, a technique in which scientists release a harmless tracer dye into the water entering the cave at the surface and then look for that dye emerging at the springs on the coast, has suggested that the water system in the Arabika Massif may extend to depths beyond what has been physically reached. Some estimates based on this tracing work suggest the system may descend to 2,100 meters or more below the surface, which would mean that below the deepest point any human has reached in Veryovkina, below the 2,212 meter survey mark that currently defines the deepest known cave on Earth, there is more cave, unsurveyed, unreached, not empty, filled with cold water and narrow fractures and the slow movement of the hydrological system that has been building this place for millions of years. But a more cave. Dye tracing is an imprecise science at these scales. The dye tells you that the water is connected. It does not tell you whether the passages the water moves through are physically large enough for a human being to enter. Much of what lies below the explored sections of Veryovkina and Cueva may be flooded passages, cracks in the rock too narrow to traverse, galleries filled with sediment. The water finds a way through. That does not mean a person can. But the possibility that the true hydrological bottom of the Arabika system lies deeper than any surveyed point is a real possibility, supported by evidence. And it means that the category of deepest cave is not a fixed thing. It is an active frontier. This is perhaps what most distinguishes cave exploration from other forms of exploration at the extremes of what is physically possible. The highest point on the Earth's surface is unambiguous. The depth of the Mariana Trench is measurable, but the depth of a cave is a function of how far a human expedition has been able to descend into a specific system under specific conditions, and the system may extend well beyond that point. The record is not the limit of the cave, it is the limit of what we have reached inside it. These are different things. Mammoth Cave in Kentucky holds a different kind of record. It is not the deepest cave, it is the longest, with more than 660 kilometers of surveyed passages, a number that has grown continuously as exploration continues, and that is expected to keep growing. The longest and the deepest are almost never the same cave, because the conditions that produce great length and the conditions that produce great depth are geometrically different. A long cave extends horizontally through a karst system, following dissolution channels through layers of soluble rock over vast distances. A deep cave plunges vertically down through the fractures and shafts of a massif where the rock is thick and the structural conditions allow vertical continuity. Mammoth Cave spreads. Veryovkina drops. The two records together describe a kind of underground geography that most people will never encounter directly, but that exists, real and specific, below the landscape we occupy. The planet is not solid beneath its surface, it is riddled. The limestone regions of the Earth, the karst, the Arabika Massif, the Appalachian Plateau, the limestone mountains of southern China, the karst of southeastern Asia, the chalk and limestone of Britain and France, are all threaded with passages and chambers and shafts carved by water over timescales that dwarf the entire history of our species. And we have explored with all our technology and all our capability and all our decades of systematic caving a fraction of what is there. We have mapped the surface of Mars in finer detail than the interior of the Arabika Massif. This is not a rhetorical flourish. Orbital instruments can map a planetary surface with a completeness and resolution that no surface expedition could match. And Mars has been orbited and studied and imaged in extraordinary detail. The interior of a deep cave system, by contrast, is accessible only to a human body moving through it in real time, managing ropes and anchors and cold and water, with instrumentation limited to what can be carried on that body into conditions that are at the edge of what the body can sustain. Mars is far, but we know its surface. The bottom of Veryovkina is close. It is on our own planet, a few hours' drive from the Black Sea coast, and we are still working out where it is. The record stands at approximately 2,212 meters. The next expedition will go down. The water will be there when they arrive. The shafts will be cold and wet and vertical and long, and at the bottom of the last surveyed passage below the deepest camp, at the furthest point any human being has ever been inside the Earth, the water will still be moving, through fractures too narrow to enter, through passages we do not know about, toward springs on the coast that the dye has already told us are connected, carrying the cave's secrets in the direction of the sea, patient and silent and indifferent, the way limestone hydrology has always moved, the way it was moving long before anyone arrived to measure it, and the way it will move long after the last expedition has come back up to the surface and the record has been written down and changed again and written down again. Cristales is there in the same massif, only 15 meters shallower or thereabouts by current measurements. Two caves in the same limestone, fed by the same rain, draining to the same springs, each one pushing the other toward a record that is always, by the nature of the system, about to be provisional, and somewhere in the Arabika Massif, at a depth that has not yet been reached, the water keeps going. You could spend a very long time sitting with that. But the dark is not the only strange place the Earth has prepared for you. And the cold, vertical, flooding underworld of Abkhazia is not the only register in which strangeness arrives. Sometimes it arrives gently. Sometimes it arrives as light. New Zealand's North Island contains a cave that has been making people stop and look up for a very long time. The cave is part of the limestone country near a place called Waitomo. The limestone there is old, formed from the compressed remains of ancient marine creatures, and water has moved through it in the way that water always moves through limestone, dissolving and carving over millions of years into a system of passages and chambers that the Waitomo River drains through underground before emerging again into the open air. The river and the passages are real enough and interesting enough in the ordinary way of karst caves. But the ceiling is the thing. The ceiling of the Waitomo caves is covered in large portions in what appears to be a sky. A dark sky lit with thousands of small blue-green points of light spread across the rock above in concentrations and clusters that have the irregular, natural beauty of a clear night far from any city. People who float through the cave on a boat and look up at the ceiling often use the word stars because the visual impression is genuinely that, a night sky. A ceiling of stars, calm and vast and quietly extraordinary. But they are not stars, and understanding what they actually are changes the way the ceiling looks, if you let it. Each point of light is a lava. Specifically, the lava of Arachnocampa luminosa, a species of fungus gnat found only in New Zealand. It is important to note, because the common name is misleading, that these creatures are not worms. They are not worms in any biological sense. They are the larval stage of a small fly, a gnat, and they are called glowworms because they glow and because they live in caves and because the word worm, in the informal usage of 150 years of New Zealand vernacular, came to attach itself to them and has stayed. But the organism is Arachnocampa luminosa, and it is a gnat, and what it does with its life in its larval stage is one of the more elegant and slightly unnerving strategies in the animal kingdom. The larva builds a nest on the ceiling of the cave. From its nest it hangs threads. Many threads, sometimes dozens. Each thread is made of silk, and each thread is studded along its length with tiny droplets of mucus, like beads on a necklace or dew on a spider's web, each droplet spaced evenly from the next, each one sticky. The threads hang down from the ceiling into the cave's air column, and they glow. The lava itself glows, and the light it produces has a color in the blue-green range, and this light is visible in the darkness of the cave to anything that is flying through that darkness. And what flies through the darkness of the Waitomo caves? Insects, flies, midges, the winged adults of various cave-dwelling species, all of them navigating in the dark and drawn, the way many flying insects are drawn, toward light. Light in a dark cave is unusual. Light in a dark cave that appears to come from above, from a ceiling studded with blue-green points, is something a flying insect navigating by instinct and chemistry interprets as sky, as the open sky above the cave entrance, toward which upward flight through a dark tunnel would lead. The insects fly toward the light. They fly up toward the ceiling where the lava waits, and they fly into the threads. The mucus droplets are sticky. The thread, once contacted, holds. The insect caught struggles and signals its struggle through the vibration of the thread, and the lava above, feeling that vibration, hauls the thread up and consumes what it has caught. The ceiling of the Waitomo cave which looks to a human visitor floating beneath it in a boat like a night sky full of gentle stars, is in functional reality a killing flaw. It is a three-dimensional array of individually operated sticky traps, each one baited with light, each one tended by a larva waiting for the vibration that tells it something has been caught. The beauty is the trap. The two things are the same thing, and you can know that you can hold both truths in mind simultaneously, the beauty and the mechanism. And the ceiling is still beautiful. If anything, it is more interesting because the question of how and why this works opens into a set of questions that biologists are still genuinely working through. The light itself comes from a chemical reaction. The larva's light organ is located in a modified portion of its excretory system, which is to say, the organ that produces the light is derived from the organ the animal uses to process waste. The light is produced through the interaction of a chemical called luciferin with an enzyme called luciferase, a pairing that appears across many bioluminescent organisms, from fireflies to deep-sea fish, in various forms. The reaction produces light with very little heat, which is the key to its efficiency. A warm light source in the body of a small larva would cook it. The cold blue-green glow of luciferin luciferase produces light without significant heat, and the larva can sustain it continuously without burning up. But the precise details of how Arachnocampa luminosa manages its light, how the intensity is regulated, how the larva knows to glow brighter when it is hungry, what exactly triggers the increase, remain subjects of ongoing study and some disagreement. The luciferin in this species is chemically distinct from the luciferin in a firefly, which means the firefly's well-studied biochemical pathway does not translate directly. The New Zealand glowworm has a separate evolutionary history of arriving at the same solution, light as a tool, through a different chemical route. And that parallel evolution, the fact that bioluminescence has been invented independently in multiple lineages across the tree of life, raises questions that biologists are still circling. What is it about certain chemical environments, certain metabolic pressures, that keeps producing light as an answer? In the Waitomo cave, the observation that hungrier larvae glow more brightly is well established. It is one of the more poetically strange facts in the dossier of animal behavior. The animal that needs food most urgently expends more energy to attract it. The logic is sound. A brighter lure catches more prey, and the benefit outweighs the metabolic cost when the alternative is starvation. But the mechanism by which the larva modulates its own light output, whether it controls the supply of luciferin, or the activity of luciferase, or something further upstream in the chemistry, is not fully resolved. And there is the question of the colony as a whole. When you look up at the ceiling of Waitomo and see what appears to be a sky of stars, you are looking at thousands of individual larvae, each operating its own silk lines, each producing its own light, each waiting for its own prey. But the ceiling is not random. There is a spatial organization to it, a distribution that suggests individual larvae are maintaining something like territory. The silk lines of one larva do not generally become entangled with those of its neighbor, which would reduce the efficiency of both. Whether they are actively responding to the presence of neighboring glow, whether they can in some sense see each other's light and adjust their own behavior in response to it, or whether the spacing emerges purely from mechanical competition for ceiling attachment points is not certain. The question of what the individual larva knows about its neighbors is open. What is certain is the rest of the larva's life, which is, in its later stages, brutally brief and functionally catastrophic. The larva spends most of its existence in the glowing, silk-spinning, prey-catching phase. Weeks, sometimes months, depending on food availability. Then it pupates, hanging from the ceiling in a translucent casing while it reorganizes itself entirely. And then it emerges as an adult. The adult Arachnocampa luminosa has no functional mouth. It cannot eat. It exists solely to find a mate, reproduce, and die, usually within a few days, living on the reserves stored during its larval phase. The adult that emerges from the pupa has precisely one task and no equipment for any other. Life, for this animal, is essentially over at the moment it achieves its adult form. Everything that the creature is, the engineering, the chemistry, the behavior, the light, was built for the larva, not the adult. Among larvae in crowded conditions there is cannibalism. A larva that runs short of prey or that finds itself next to a newly pupating neighbor will sometimes consume what is available. The glowing ceiling is not only a trap for insects, it is an environment of quiet competition among the trappers themselves. You float beneath this on a boat, in a cave in New Zealand's North Island, in the silence that the guides request. Because noise disturbs the larvae, and too much carbon dioxide from too many visitors can suppress the glow. And you look up at what feels like an open night sky, and you know that every point of light up there is a larva hanging from a silk thread, waiting, and that somewhere in the ceiling above you a smaller organism has been caught in one of those threads and is in the process of being consumed, and that the beauty and the death are the same event, and that the precise chemistry by which the light is produced, and the question of how the colony organizes itself, and the reason that evolution keeps discovering light as a solution across such different lineages, are all genuinely open questions that biologists are still working on. Arachnocampa luminosa has been observed and studied for a long time. It has not been fully explained. That is the cave at Waitomo, a ceiling that is simultaneously a wonder and a weapon and a set of biological questions that the ceiling itself has not yet finished answering. There is one more cave. It sits in a mountain range in Austria called the Tennengebirge, in a section of the Austrian Alps not far from the town of Werfen, and its name in German means, roughly, the world of the ice giants, Eisriesenwelt. And if you expect a cave with that name to be uniformly, deeply, permanently frozen, a place where the cold intensifies as you descend, where ice clings to the walls the further in you go, where the temperature drops steadily with depth as it seems intuitively it should, then the cave will surprise you immediately. Because the Eisriesenwelt is cold only at the entrance, it warms as you go deeper. The ice is concentrated near the door. This is the first thing the cave teaches you, and it is a good lesson to carry. The rule that seems obvious, deeper means colder because you are further from the sun, is not universal. In Eisriesenwelt, it is wrong, and the reason it is wrong tells you something about how air behaves in stone, something that turns out to matter enormously for how any ice cave forms and persists at all. The cave stretches approximately 42 kilometers into the mountain. It is the largest ice cave in the world by extent. 42 kilometers of passage running deep into the Tennengebirge. But only the first approximately 1 kilometer of that passage holds ice. The remaining 41 kilometers, give or take, are ordinary limestone cave, dark, humid, and actually warmer than the entrance, maintaining the relatively stable temperatures that rock produces when it is insulated from the surface by sufficient depth of mountain. If you walked into the Eisriesenwelt and kept going past the ice, past the frozen formations, past the great sculptures and frozen cascades that make the front section extraordinary, you would emerge eventually into stone passages that hold no ice at all, that are not unusually cold, that are, by the standards of what a cave is supposed to be, unremarkable. The spectacle is at the entrance, and it is there because of what is called the chimney effect. Think of the cave as a long tube running into the mountain. In winter, cold air from outside sinks into the cave. Cold air is denser than warm air, and so it flows downward, pooling in the lower sections of the cave entrance, filling the passages near the door with air that is as cold as the winter outside. That cold air sits in the rock and chills it. The rock, which takes months to respond to temperature changes because stone changes temperature slowly, absorbs the cold of winter and holds it. The walls near the entrance become cold. They stay cold. Then spring comes, the outside air warms. Meltwater from the snowfields above begins to seep through the limestone and find its way into the cave, and it finds walls that are still cold, cold from the winter air that pooled there for months. The meltwater touches cold rock and freezes. It does not trickle to the floor and puddle there. It meets the cold stone and becomes ice on contact. Slowly, through the spring and into the summer, layer after layer of meltwater freezes against the cold entrance walls, building upward and outward and inward, forming the formations that visitors see. Great curtains of ice, columns, frozen pools, what looks like a waterfall stopped in the moment of its falling, held in translucent blue-white suspension. In summer, the outside air is warm enough that a different movement takes over. Warm air rises through the cave and exits from upper openings, and the flow reverses, and the ice near the entrance is partially melted and reshaped. In autumn and winter, the cycle begins again. Cold air sinks, the rock is chilled, the stage is set for the next season's meltwater to freeze. This is the chimney effect in an ice cave. The cave breathes with the seasons, and the breathing is what makes the ice. The deep, warm sections beyond the ice zone are insulated from this seasonal breathing. The entrance section is fully exposed to it, which is why the ice is at the door. Anton Posselt formally explored the cave in 1879, though local people had known of its entrance long before. He descended into the ice section and reported what he found, and the cave became a subject of curiosity and then of systematic investigation. It was Alexander von Merck who mapped it in the early years of the 20th century, who spent years going deeper into the mountain, surveying the passages, understanding the layout of what turned out to be an enormous system. Von Merck was devoted to the cave in a way that went beyond professional interest. He returned to it repeatedly, pushed further into it, gave much of his time to understanding it. He died in the First World War at the Battle of the Isonzo in 1916. His friends and fellow cavers brought his ashes back to the cave he had loved and interred them there. Alexander von Merck is buried inside Eisriesenwelt. His ashes rest in the mountain he spent years mapping. When visitors carry their lamps through the ice section today, handheld lights, since the cave's sensitivity to any permanent installation means that the illumination of each visit is temporary and portable, they are walking through the passage that von Merck surveyed by the same kind of light more than a century ago. The ice he walked past has been replaced many times over by the cycling of seasons. But the chamber shapes he mapped are the same chamber shapes. The cave remembers him in the way caves remember things, not through any record the stone keeps deliberately, but through the simple fact that stone does not change quickly, and he was there. Now, the scientific argument about Eisriesenwelt is one that is familiar in outline but particular in its details. The question is what the ice is doing in response to a warming climate and what that means. Ice caves like Eisriesenwelt are sensitive recorders of climate. The thickness and extent of the ice formations, the number of seasonal layers preserved in the deeper ice deposits, the temperature at which the entrance walls stabilize each winter, all of these are connected to broader patterns of temperature and precipitation. If the winters are milder, the entrance walls are chilled less thoroughly, and there is less cold surface area for the spring meltwater to freeze against. If the snowfields above the cave are smaller, there is less meltwater to seep through. If the summers are longer and hotter, more of the entrance ice melts each year than can be replaced by the next winter's cycle. Whether Eisriesenwelt's ice is currently stable, growing, or shrinking is a question that researchers have examined and continue to examine, and the answer is entangled with questions about exactly how the chimney effect responds to the specific regional climate patterns of the Teningebirge, and how measurements taken over different periods compare to one another. The ice in the front of the cave is not a static object. It is an ongoing negotiation between the cold that winter deposits in the rock and the warmth that each summer tries to reclaim. The balance of that negotiation over decades and centuries is what climate has always determined. What the ice also preserves in its layered structure is a record of that negotiation going backward in time. Each layer of ice represents a season, a year, a particular balance of cold and melt. Read the layers carefully as researchers read ice cores from glaciers and polar sheets, and you are reading a compressed history of climate in this mountain. The cave holds its own archive. The question of whether it is growing or retreating is partly a question about what the archive records and what the most recent pages tell us. This is the last lesson the Eisriesenwelt offers. The cave that seems at first to be straightforwardly about cold and ice and the obvious beauty of frozen things turns out to be a climate instrument. The chimney effect that produces the ice is itself a finely calibrated system, sensitive to the average temperature of winter, the amount of snow above, the length of summer. And the layer of ice at the cave's entrance is a slow-motion recording of all of those variables going back through time. The ice is not just beautiful, it is data. And data, like everything else in these 7 caves, is something that scientists are still reading and still arguing about and still revising as new measurements come in. So, 7 caves, 7 places where rock and water and time and chance produce something that doesn't fit the pattern, something that breaks a rule so fundamental that when it was found, the people who found it had to stop and reconsider what they thought they knew. Movile, sealed for 5.5 million years beneath clay near the Black Sea coast, running on sunlight it has never seen. Its peculiar blind community of creatures eating the floating mats of bacteria that eat sulfur and methane rather than anything derived from a green plant or a ray of light. The question of how old that community is and whether any trace of the surface world still seeps in has not been settled. What has been established is that an ecosystem can run entirely on chemistry, on the energy locked in molecules underground, with no photon of sunlight involved at any stage. We thought we needed the sun. Movile says the sun is optional. The crystals of Naica, grown in slow mineral stillness over hundreds of thousands of years, in a room that would kill an unprotected person in 20 minutes, 11 meters long and heavier than most delivery trucks, products of a temperature so precisely stable that only the thinnest margin between 2 chemical states, anhydrite above, gypsum below, allowed them to form and keep forming over all that time. And inside those crystals, in pockets of ancient fluid, something that researchers found and reported as possibly alive, microbes apparently dormant for tens of thousands of years. Whether those microbes are genuine ancient survivors or modern contamination introduced during study is a question that has been raised and not definitively resolved. The crystals grew in conditions we cannot replicate. The life inside them, if it is life, waited in conditions we cannot fully imagine. Son Doong in Vietnam, the largest known cave passage on Earth by volume, with its dolines open to the sky, its jungles growing inside the mountain, its clouds forming in the transition between warm cave air and cooler outside air, its hidden river and its calcite wall, and somewhere beneath it, flooded and still being explored, a connection to another cave system that may make the total volume larger than anything currently measured. We do not know the full extent of Son Doong. We know where we have been. We do not know what is beyond where the divers turned back. Lechuguilla in New Mexico, carved not by rain and rivers dissolving it from above, but by sulfuric acid rising from oil deposits below, eating the limestone from the inside. A mechanism that scientists understood poorly before Lechuguilla demonstrated it so clearly that the textbooks had to be revised. And in the darkness of that sealed cave, bacteria that have never encountered a hospital or a pharmaceutical laboratory or a prescription, carrying resistance to antibiotics that were invented in the 20th century. The resistance predates the drugs by millions of years. It is natural, it is ancient. And what it implies about the resistance crisis that medicine faces now, about where resistance comes from and how permanent it is, remains a question with significant stakes and no settled answer. Veryovkina in Abkhazia, currently the deepest known cave on Earth at approximately 2,212 meters, overtaking its nearby rival Cristales by a margin so small that the two records have traded places before and may trade again. The cavers who reached the bottom in 2018 did so after multiple days underground, through cold and wet and dark, and on the way back up were nearly trapped by a flash flood that surged more than 100 meters up the shafts in the time it took them to begin their ascent. Dye tracers poured into the cave suggest the water system continues downward beyond what has been explored, possibly to depths of 2,300 meters or more. The bottom the cavers reached may not be the bottom of the cave. We do not know where the actual bottom is. We have mapped the surface of Mars in more detail than the floor of this cave. Waitomo in New Zealand, where Arachnocampa luminosa, a fungus gnat, not a worm, the name a piece of common usage that the biology corrects, hangs from the ceiling of a limestone cave and produces cold blue-green light through a chemical reaction in an organ derived from its own excretory system, and dangles beaded silk threads below itself, and waits, and the waiting is predation, and the beauty is the trap. And the question of exactly how the larva regulates the intensity of its own light, and how the colony organizes its spacing, and why evolution has invented bioluminescence independently so many times across so many lineages, is a set of questions that biology is actively working through. The adult animal that emerges from this system after weeks or months of patient luminous hunting has no mouth. It cannot eat. It lives only to reproduce, and then it is gone. Everything the creature built was built for the larva. And Eisriesenwelt, the world of the ice giants, 42 kilometers into the Teneriffe Mountains near Werfen in Austria, where the ice gathers not at the deepest point but at the entrance, because cold winter air sinks into the cave and chills the rock, and the spring meltwater finds that cold rock and freezes against it, and the cave breathes with the seasons in a chimney effect that deposits ice at the door and leaves the deeper passages unremarkably warm. Alexander von Merck mapped it 100 years ago and never came home from the war, and his ashes rest in the cave he loved, and the ice that surrounds them has cycled through dozens of winters since he was placed there, and the question of whether it is growing or retreating, and what the layers of that ice record about the climate of the mountain over centuries is one that researchers with instruments and ice cores are still working out. 7 caves, 7 arguments, 7 places where the planet declined to behave as expected. And what unites them is not size or beauty or age, though they are large and often beautiful and very old. What unites them is that each one broke a rule we had assumed was load-bearing. A rule so basic, we hadn't even been conscious of treating it as a rule, that life needs sunlight, that crystals cannot grow so large, that a cave cannot have its own climate, that rock dissolves only from the outside in, that we know where the floor is, that a light so beautiful could be so purposeful and so lethal at once, that cold lives deepest. Each cave required something to be reconsidered, not minor adjustments, the kind of reconsidering that sends someone back to the beginning of a model and starts again. Movile changed the way we think about life's dependence on the sun and by extension changed the way we think about where life might exist on other worlds. Lechuguilla changed the way we teach the formation of caves. Naica asked whether the limits of biology, or the length of dormancy, the conditions under which life can persist, are where we thought they were. Son Doong reminded us that the surface of this planet, even now, contains spaces we have not entered and cannot yet measure. Veryovkina reminded us that the depth of this planet is not mapped. Waitomo reminded us that evolution finds the same solutions by different routes, that beauty and function are often the same thing, seen from different angles. Eisriesenwelt reminded us that counterintuitive things are real, that the obvious answer is not always the right one, and that a mountain can hold a climate record in ice that it has been quietly keeping for centuries, whether anyone was reading it or not. The planet has been doing all of this without us. The crystals in Naica grew through the long human prehistory, through every civilization we have built and lost, through everything we have learned and forgotten, in a room that was too hot for any person to enter, and that no person knew existed until the year 2000, when miners draining water from a chamber found themselves looking at something that had been growing for 500,000 years in the dark. The microbes in Lechuguilla had been evolving their resistance mechanisms through geologic time, through epochs of deep quiet, accumulating biochemical capabilities that we only discovered we needed to worry about when we invented the drugs they were already resistant to. These things were not waiting to be found, they were simply there. The finding was incidental, accidental, a power plant being built near Mangalia, a mining operation near Naica, a man named Ho Khan in the forests of Phong Nha-Kẻ Bàng who heard wind coming from the earth. The planet was not concealing them deliberately. It was merely large and old and full of processes that do not require observation in order to continue. There is something in this that is worth holding as you drift off tonight. Not an anxious thought. There is nothing threatening in these caves, nothing that reaches up through the stone toward you. Quite the opposite. The thought is a settling one, if you let it be. The world is older than any anxiety you carry. It has been building crystals in the dark for 500,000 years and generating ecosystems without sunlight for 5 million years and recording climate in layers of ice for centuries, all without reference to anything you or I have done or not done or meant to do. The caves are not indifferent to us in a cold way. They are simply continuous. They were here before us. They will be here after. And we have explored perhaps a fraction of them. The passages of Veryovkina go further than we have followed. Son Doong connects to something beneath it that divers have not yet mapped. There are, almost certainly, caves on this planet that no human has entered, some that no instrument has detected, some beneath rock that still waits to be broken open by water or by accident or by the kind of patient geological force that works on schedules measured in millions of years. We share this planet with systems we cannot yet describe. That seems tonight like a good thing to know. If you are somewhere in the world listening to this, in a city or in the country, in a room that is dark or nearly dark, with the particular sounds that belong to your particular place seeping in at the edges, then you are somewhere above rock that has been behaving in ways we don't fully understand for far longer than we have been here to notice. Below wherever you are, the geological processes that made these caves and every other cave are continuing. Water moves through limestone in the dark. Minerals in solution precipitate out of groundwater at temperatures we can barely maintain artificially for 20 minutes. Air moves through mountain passages according to seasonal pressures that no one planned and no one controls. Life, in places where the light has never reached, oxidizes sulfur and methane and builds ecosystems out of chemistry alone. The floor you are lying on rests on stone, The stone goes down. We do not know how far. If you feel moved to share where you are in the world tonight, which country, which coast, which side of the mountain, the comments are there, and I read them. There is something genuinely interesting to me about the map that those comments make. The places where people listen to slow accounts of strange caves, the rooms and circumstances, the geography of a quiet night. If you are new here, there are more of these, long, slow descents into places that are old and strange and genuinely puzzling at a pace that is meant to let you drift. Subscribe if that sounds like something you want to come back to. History will still be here in the morning. For now, rest.